want to take a look at the graphs of r equals sine theta and r equals cosine theta here in polar coordinates. And I want to do this in a way that doesn't use tables so much. So what I have here is I've got r equals, well, 3 sine theta. And the graph here in red is the way I would graph it like we did earlier in the quarter. If you think of the axis here being theta, I'm using t just because it's hard to find a theta on the keyboard. So theta is running this way and r is going this way. So I'm just thinking of this as a regular old Cartesian graph. Theta versus r like it were x's and y's, and the graph of a sine curve passes through the origin. It's got period 2 pi. You can see just a little bit more than 6 here. 6.28 is where it ends its cycle. The highest point here is where the amplitude of 3 gets to, and the lowest is -3. So what this does, this acts for me like my table, in that if you tell me what theta is, I can figure out what r is. Then over here I'm going to plot that in polar coordinates. I'm going to turn through an angle of theta and move a distance of r. In fact, when I animate this here, you'll see a couple of things happening here. So let's see how this goes. So I'm starting off here with an angle that's getting bigger. Over here I just move over whatever that angle is. This is the height I'm trying to plot, and so this black line segment is the same as the length of that line segment over there. Okay? So whatever this height is, that's what I'm using for r. The angle that I'm turning through is whatever this distance along this theta axis is. Okay? So I can watch it get up to its highest point. Oops, not quite the highest point. There we go. There's the highest point at pi over 2. You're up at a distance of 3. So when the angle is pi over 2, I'm up at 3. By the time this comes back down to pi, by the time the angle gets over to pi, the radius is going to come back down to 0. So by the time I'm looking in the direction of pi, in fact you can see that little red segment showing me what direction I'm looking. Looking in the direction of pi, I have an r of 0. So I've started with r of 0, gone out to r equals 3, and come back to r equals 0. As I was turning, I went from r equals 0 out to r equals 3, and then back down to r equals 0 again. So by the time I turned halfway around, I've done a loop there. Now, as I'm looking into the third quadrant here, thetas start becoming negative. So I'm over here looking into the third quadrant, but with these negative, sorry, theta is not negative, r is negative. As r is this negative value down here, I'm plotting behind me. Looking into the third quadrant, but plotting behind me because r is negative. Right? In fact, it gets all the way down to -3 right there. There we go. R is -3. And so I'm looking in the direction of 3 pi over 2. That's where this is, 3 pi over 2. With an r of -3 plots me back up here again. Okay? And then I go into the fourth quadrant. I'm looking into the fourth quadrant, but again, r is still negative. So though I'm looking in the fourth quadrant, I'm plotting back there in the second quadrant. And it keeps going until I get to there. With my angle being 2 pi, my radius has come back to 0, and then it just repeats itself. Okay? So though it looks like I should have a big positive pedal and a big negative, a big positive loop and a big negative loop, I see only one, but that's because they're both on top of each other. This looks a lot like it might be a circle. And in fact, in another video, we'll do the algebra here of this and find that yes, indeed, it is a circle. That if we convert this equation, r equals 3 sine theta, into x's and y's, we can show that it's a circle centered somewhere up here, and the radius is just enough to make it pass through the origin. Okay. Some quick things here. I noticed that the 3 is just changing the amplitude, and if I change this here, the red graph is just going to change the amplitude. So I'm going to change that 3 to 2. It's going to be a little bit shorter. What happened here? It didn't get as far away. Right? It looks like a little bit smaller circle. If I make that a 1, this is even smaller amplitude, and this gets even smaller. It's still that 1 loop there, and then I got this other loop as it goes. I think of the loops as happening when r goes from 0 to something away from 0 and it comes back to 0. You've moved out and then you come back to the origin again. Right? There's that big old loop. Right? And it turns out this loop happens to be perfectly circular. Right? I'm going to go back to 3 just to make it a taller thing and easier to see. At this time, though, I'm going to switch from sine to cosine. Okay. Now I look at this red graph over here. Again, this acts as my table. This is my, hey, you tell me what t is, I can figure out what r is. And then I can plot it over here. But I can see a lot of stuff. I can see that the radius is going to start up here at 3. It's going to dip down to 0. It's going to go down to -3. It's going to come back to 0 and up to 3 again. All that as theta is ranging from 0 to 2 pi. So as I move in a circle, the radius has to change from big to 0 right there. The radius is negative, what we're looking at now, back to 0, and then starting to get positive again, and we get back to 3 and start all over again. Okay. Negative values of the radius. Okay. So this one, when we're looking up here in the first quadrant, r is positive. Starting at 3, coming down to 0. So by the time the angle gets to pi over 2, not quite pi over 2, there's pi over 2, the radius is down to 0. So in that first quadrant, you've drawn this part of a loop down to 0. Now, as we go into the second quadrant, the r is becoming negative. So although I'm looking into the second quadrant, the negative r's mean I'm plotting down into the third quadrant. By the time you get to pi, you're at the lowest point on this cosine curve, means you're the most negative. Looking in the direction of pi, I'm plotting -3. So looking that way, backing up 3 gets me over here. Okay. As I move into the third quadrant, the r is still negative, but coming closer to 0. So this black line segment is shrinking its length. It's always the same as that black line segment. All the way down to 0 right there. Now I'm looking into the fourth quadrant, and the fourth quadrant is giving me these positive r values, and so I'm plotting in the same direction that I'm looking. R is getting bigger and bigger and bigger until I get back up to 3 right there. Okay. This also is a circle. Maybe not immediately obvious that it's a circle, but we'll do some algebra to show that that is indeed a circle. Okay. There's sine and cosine in polar coordinates. While I'm here, I got a little more time, I want to look at secant and tangent. So if I were to look at secant, actually I want to look at secant and cosecant. Let me just make this a 1 here. This looks like a straight line. Could that really be a straight line? Well, we're going to do some algebra again in another video and show that it is a straight line. Likewise, if I put in the cosecant, not CSC, how about, sorry, SCS, CSC cosecant. This one now looks like a line that's horizontal. Huh. It is in fact a line that's horizontal. We'll show that in the next video. While we're here, let's do tangent and cotangent too. These are a little goofier. The tangent looks like this. These things head off to infinity. There's a question of whether these keep opening up wider and wider, or do they start coming back together again. They actually just approach a vertical asymptote. The vertical asymptote is, I believe, 1. Yeah, x equals 1 is the line here that's a vertical asymptote for this, and x equals -1 on the other side. Okay. That's the graph of the tangent function. R equals tangent theta. Not something that we use very often, just kind of an oddity. Likewise, the cotangent looks similar, probably going in the other direction. Sure enough, going the other way. Okay. Y equals 1 and y equals -1 will be the horizontal asymptotes for that thing. You can see it with positive r's or with negative r values, right? When the red and the black are in the same direction, r is positive. When the red and the black are in opposite directions, r is negative. So the red's always showing what direction you're looking in. Anyway, there's some graphs of the trig functions in polar coordinates.